Hi, I welcome you back to this wonderful journey of learning structure analysis with STAAD.Pro. I am Sudeep and I am a structural engineer and the leader of the STAAD.Pro technical team at Bentley Systems. I have been working on STAAD.Pro at Bentley for 17 years now, and prior to that, I have 6 years of experience as a structural designer. So do not miss out on this opportunity of learning STAAD.Pro with clear concepts from an expert. Now, we are learning about the modeling properties and materials in STAAD.Pro. In the last couple of sessions, we had learned about the default beta zero orientation of the local axis system of the members. Now, for modeling of sectional properties, we need to assign sections to the members. In this session, we will try to understand how certain sections that are used in concrete structures are oriented with respect to the local axis system. But before we go forward, please take a moment to hit the subscribe button if you are new to this channel and join us in this wonderful journey of learning structural engineering with STAAD.Pro. And if you have been around in this channel, give it a big like if I had been able to provide some value. We will start with the most common concrete section, the rectangular section. So what you see on the screen are the positive direction of the local y and local z of a member, depicted as Ly and Lz respectively. As you understand by now, the positive direction of the local x-axis is coming out of the screen towards you. Now, if a rectangular section is assigned to a member, the rectangular section will be oriented like this with respect to the Ly and Lz axis. The dimension parallel to the local z is called the ZD dimension, and the dimension that is parallel to the local y axis is called the YD dimension. From the analysis perspective, it does not really matter as to which is the depth and which is the width of the section, as the member forces will be reported with respect to the local axis. Note that local y and local z will represent the principal axis of the rectangular section. However, there is no specific requirement that Lz or Ly has to be the major or the minor principal axis. Either of them can be major or minor principal axis, which would be dependent on the dimensions Yd and Zd. For example, the section on the left would have Lz as the major principal axis and Ly as the minor principal axis. And the section on the right, on the other hand, would have the Lz as the minor principal axis and Ly as the major principal axis. I hope you remember the concept of the principal axis that we had discussed. If not, you can access that session by clicking on the link that is appearing on the screen right now. However, from the design perspective, if you want to do a design of concrete section in addition to the analysis, then ZD has to be specified as the width and YD has to be specified as the depth of the section to get a correct distribution of the reinforcement in the section. From this perspective, Lz has to be the major principal axis and Ly has to be the minor principal axis. The next section we will consider is the circular section. A circular section is an axisymmetric section, and thus we need to define only one term, that is the diameter of the section. We define that as YD. Remember that for axisymmetric section, all possible axes going through the center of the circular section will have the same moment of inertia. Now that we have discussed the orientation of the common concrete cross sections, let us discuss about the orientation of few other sections that are used in concrete design, but not very common. So we will start discussing the T section. T section is defined by 4 parameters: the width of the flange ZD, the overall depth of the section YD, the width of the web ZB, and the depth of the web YB. Again, note that all dimensions represented with Z are oriented along the Z axis, like ZD and ZB. And all dimensions represented with Y are oriented along the Y axis, like YD and YB. Also note that the dimension ZD would be located along the positive direction of the local Y axis from the centroid of the section, and the dimension ZB would be located along the negative direction of the local y-axis from the centroid of the section. It's important to note that for T sections, the local z-axis represents the major principal axis, while the local y-axis represents the minor principal axis. You have to go back to our discussion on the principal axis to understand how the local y and local z represents the principal axis system of a T section. Next, we'll discuss about the trapezoidal section. The trapezoidal section can be defined by three parameters: the larger width of the parallel sides, ZD, and then the smaller width of the parallel sides, ZB, and then the depth of the trapezoid measured as the distance between the parallel lines YD. Now, ZD and ZB, I had explained that as the larger and the smaller sides of the trapezoid respectively. However, the larger and smaller are of relative terms. Actually, ZD would be the dimension that would be located by going in the positive direction of the local y-axis, and ZB would be the dimension that would be located by going along the negative direction of the local y-axis from the centroid of the section. Again, in this case, the local z would represent the major principal axis and the local y would represent the minor principal axis. So you may have noticed that we can define all of the sections that we had discussed with the help of four sectional parameters. The following table summarizes our understanding. Rectangular section can be specified using two parameters, YD and ZD. The rest of the parameters YB and ZB does not need to be defined for a rectangular section. Circular sections are the ones that would need only one parameter YD to be specified. The rest of the parameters does not need to be specified for a circular section. T section would need all the parameters to be specified, and for the trapezoidal section we would need three parameters, YD, ZB and ZD, to be specified. Note that in all these cases, the sectional properties is automatically calculated by the program based on the dimensions specified. However, in case you want to override the sectional properties with the user-defined properties, you can use the prismatic general sections. As usual, you need to specify YD only for circular sections, YD and ZD for rectangular section, YD, ZD and ZB for trapezoidal section, and all of YD, ZD, ZB and YB for the T sections. Now, to override the program calculated gross sectional properties, one would need to specify AX for the cross-sectional area, AY and AZ if you want to override the program calculated values of shear area along the local Y and the local Z axis. If you want to override the torsional constant, you need to specify your value using IX, and you need to specify IZ to specify the moment of inertia about the local Z axis, and IY as the moment of inertia about the local Y axis. Now, remember that this would be required only if you intend to override the program calculated value. Else, if you do not specify any of this, the program would automatically calculate the sectional properties based on the sectional dimensions that you have specified. In the next session, we will learn about specifying the concrete sections and concrete materials to the members in STAAD.Pro environment. An understanding of what we have discussed in this session will be very helpful in understanding the concepts. I hope you have enjoyed whatever we have discussed today. Please hit the like button if you have enjoyed whatever we had done today. I hope to see you again in the next session next week. Till then, bye.